Hello, everybody. So in our last activity, we figured out what a Newton was, right? We defined a Newton. We did a little lab where you were trying to figure out how much force in newtons you had to apply to a 1 kilogram cart to make it accelerate at 1 meter per second squared. And if we look at the results that we got out of that lab, you will see that everybody's force was pretty close to one another. See how those are all really close? Right? And on average, it was about to 3 sig figs, 0.995, which to 2 sig figs is a nice round 1. Right? So it looks like, or 1.0. So it looked like it would be about 1 Newton to make a 1 kilogram object accelerate at 1 meter per second squared. And that is, in fact, how the Newton is defined. Right? A Newton is a kilogram meter per second squared. That kind of begs the question, why? Why does it take 1 Newton to accelerate a 1 kilogram object at 1 meter per second squared? Well, for that, we're going to need to figure out how those 3 variables are related to one another. And if you remember, we came up with these 3 variables as related to the acceleration. Right? That if we change the net force or we change the mass, we thought it might change the acceleration. So this is a 3-variable lab. If you remember your lab theory, when you have 3 variables, right, we did this back in the area of a triangle lab back at the beginning of the year, right, you'll have 2 independent and 1 dependent variable. And how many independent variables should you change at a time? Only 1, because otherwise you won't know which one is affecting the dependent variable. And when you change 1 independent variable, what should you do with the other? Well, if you're not going to change it, you're going to keep it constant. So that means if we're going to have 2 independent variables, we're going to have to do 2 labs because we can only change 1 variable at a time. And then in the post lab, we'll shove them together into 1 relationship and 1 math model, as we did with the area of the triangle to find 1/2 base times height. So the purpose of today's lab is to create graphical and mathematical representations of the relationship between the acceleration, the net force, and the mass. And the math model we get out of this is known as Newton's second law, and this is one of the more important things in all of Newtonian mechanics. Right? The understanding of this math model is really fundamental to understanding why things move the way they move. So it's a really important lab. And we're going to go very high tech here, right? But we're going to have to do a 2-part lab and shove that into 1 equation at the end. So our first part is acceleration versus net force with constant mass. So we're going to change the net force that's acting, measure the resulting acceleration, and keep the mass constant. Now what are we going to use? Well, the same thing we did in the last lab. Okay? We're going to use a modified Atwood's machine. And as before, A is the smart cart, right? B is the hanging mass, hangs off the side. If we do a little force diagram of the smart cart, right, what forces act? Well, of course, gravity acting down. Notice F of G A, because it's the cart's mass that goes into the weight of the cart. The normal force, because the track is supporting the cart. Right? And those are balanced. Why? Because it's not accelerating up and down. Right? The vertical acceleration is 0. Right? No acceleration, no net force. Newton's first law. But if you'll notice, the cart is also being affected by the string, and so that's a force of tension. Now we have it set up much like we did for the last activity, which means that the net force in this case, right, is given by the force of tension. Okay, so the net force is the force of tension. The net force will be the independent variable. How could we change the net force? Well, we have to change the force of tension. And as we did in the last activity, if we want to change the force of tension, we can change the mass of the thing hanging off the side, the hanging mass, if you will. Right? So the force of tension here can be controlled by changing B, the hanging mass. Right? And we can control how much mass we put on the end of the string, which is why it's an independent variable. Don't forget here, the mass hanger, right, which these little masses hang on, is itself 5 grams. So if you look on your lab sheet, you'll notice all of the hanging masses you're going to use end in 5, and that's because you've got the mass hanger. So for example, if you're supposed to have 45 grams or 0.045 kilograms, right, you would add 40 grams to the mass hanger, and that'll make 45. Right, so don't forget the mass hanger or you're throwing things off. Okay. So the acceleration then will be our dependent variable. So when we make graphs, acceleration will be on the vertical axis, and net force, which is the force of tension, right, is going to be on the horizontal axis. Now, mass we're going to keep constant, but in these multivariable labs, it's important that we know what constant we're using. So I want you to take your cart, right? You can take the string off it, and you're going to put 4 little kind of aluminum bar masses, all right, on the cart. There's little slots for you to put these. And I want you to take the cart and the 4 masses over to the scale and measure it over to the electronic balance. Convert it to kilograms, write it on your lab sheet, right, so that we know what constant mass your cart had. Now, how are we going to measure the net force and the acceleration? The exact same way we did in the last activity. So I'll just very quickly go through it. There is a sheet on your table, right, which is how to set everything up. Just like in the last activity, you have to pair your cart to the graphical analysis to your computer. You've got to open up velocity time and force time graphs, right? And when you run trials, they will look something like this. Right? Since this is a velocity time graph, right, the acceleration is the slope. Right? So if we select when it's accelerating, and notice I don't select before you let it go, and I don't select after the masses got to the floor or after you catch the cart, and please catch the carts every single time. They're very expensive. Right? So I select the diagonal part where it is accelerating constantly because it's a linear part. Right? Apply the curve fit, and the slope here is the acceleration. Now, sometimes you have to auto scale to make it look the same so that the axes match up. All right, if I want to know the force that caused that acceleration, well, I select the same part of this graph, not after you catch it, not before you let it go. Okay, when you notice it's a completely different force, it's a higher force when it's not accelerating, because then the force of tension has to balance out the entire weight at the end of the string because nothing's accelerating. So if we take the part, kind of matching the top part when it is accelerating, and then instead of doing a curve fit, we do statistics, and we take the mean. So 0.490 newtons, right, is your average force. 0.6326 meters per second squared is your acceleration. Change the hanging mass, right, and that's going to change both the acceleration and the force of tension, the net force. Right, so that's kind of the first half of the lab. Okay, so you're going to be doing the same kind of thing you did before. Don't forget, and it does say this on the lab sheet, right, before you run any trials, disconnect the string and zero the force probe. Right, don't forget to zero the force probe. Otherwise, all your forces will be off, and you'll have to redo all of your data. You won't get the right slope, and you'll have to redo everything. Okay? So don't forget to zero the force probe. And if you do it more than once as you do the lab, it's never a bad thing to zero the force probe.